All right, guys, let's try this first one out and catch up to you. So I do say to do it both ways. I'm going to go ahead and do it both ways. If you did it the way that made more sense, that's beautiful. So this one, what's the way that makes more sense? Why does that one make more sense? So x goes from 0 to 1. That's the outer dude that's allowed to, the most of the time that's going to be just numbers. And then the inner one's got to be the one that goes between two function walls, right? So y, of course, goes from, through this whole region, it goes from this wall to that wall. Do you guys see that? So if the inner one's dy, it's got to be y equals something to y equals something. If the inner one's dx, it's got to be from x equals something to x equals something. It's got to tell you what x starts at and what x starts. So here I want to know what y starts at and where it stops. So here this would just be what to what?
X cubed to the square root of
X cubed to the square root of x, px. And then whatever the hell f is. Now again, don't do this. If I say turn them around, oh my gosh, don't do this. That's insanity. That's crazy. It doesn't make a damn bit of sense. That is somebody who doesn't understand this at all. And you're like, well, yeah, it's me. Okay, we got time. But please tell me that that does not make sense. To turn this around, you have to kind of start over a little bit. Right? If I wanted to turn this thing around, that means I want to go dx dy. So what's y do? Of course, y does what? Y goes from 0 to 1. As y does that, what does x do?
square root of x.
Careful now. X can't go from the square root of x. X goes from y squared to cube root of 1. And see how y squared is definitely the back wall? And cube root is definitely the front wall. Okay, I like it. So from the back wall to the front, from y squared to cube root of y. F of x, y, whatever the hell f is. So in this inner integral, what would be the true variable in this one?
Y.
Is it just my bad writing?
Oh,
X, right? That goes together. So x would be the true variable. Okay. This one, the way that makes more sense is to just take it. Which one would you not need to change the walls it goes between?
dy dx.
If I start here and go there, right? So that means I want to let y go crazy, and then x has to do something specific between these two function walls. Yeah. Stop there for a second. So there's the unfortunate thing is there's a lot of different ways to look at this to tell you which way to do that. That might be the best way right there is which one do I want to let be the function values? That's going to be the inner one. So x goes from there to there. The other way, oh shit, I have to break it up. Screw the other way. I want the inner one to be x. And then y goes from what to what? 1 to 3. As x goes from oh shit to oh shit.
3 minus y over 2.
Yeah, so x equals 3 minus y over 2. That sounds good. And what about this one? 2y minus 1. Yeah. Okay, so it would be from 3 minus y over 2 to 2y minus 1. That's what x does. As y goes from 1 to 3, any value of x in between there goes from this wall to that wall, but it's got to be in terms solved for x. It has to tell me what x is doing. Yeah, like it. Hey, Mike. Okay. I don't know if you guys can tell, but I just stole these pictures from various places, and that's why they're looking. Now this one, what walls would stay the same throughout the whole region?
dy dx.
Yeah, so if I let y be the one that goes between two function values, that's nice because that's how they're defined already. So that means I want to let the outer one be x, because what does x go from to? -3 to 1. So as x goes from -3 to 1, any x value in there, y is going to go from this wall, 2x, up to,
3 minus x squared.
and then whatever the function is. Now if I wanted to turn that around, what would it require?
Another
Two integrals. And I'd have to solve those for x, right? And of course that involves like a positive and negative for that parabola. That's when you solve for x now, when you get a plus or minus. So the back wall and the front wall for that parabola. I'd rather not do that. Are there situations where I have to do that? Hell yes. It depends on what f of x, y is. That's your last consideration, really, is if I set it this way, that's nice for my limits, but does my function actually integrable? Is it integrable over those limits? Sometimes, no. So then you have to turn around. Shit. I guess that would be the next level. So right now I just want you to see the flexibility and how you set at the limits. The next level would be, what the hell is that function? So that's why this next problem is the way it is. That's the next level. I don't know, did anybody make it this far? No. Just look at that integral. What would you need to do to be able to do that? Yeah, you could try tricks up, right? Which would involve letting x squared equal something. And I don't know if you've ever done a problem like that before. Yes? Good. Would you rather not do that? So that's the key. Sometimes the way it is, it's impossible. So if it was like e to the x squared inside, that's the standard one you all should realize is an impossible one. In fact, in 280 you found out it's got no like closed form. It's got to be an infinite sum answer for that. Blah, 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 blah. And so when I say why must we switch the limits, it's more of a why would we want to switch the limits. So how do I switch the limits here? So that means I want it to go now, I want to go integral
0 to 2.
dy dx. Yeah, so x is going from 0 to 2, I love it. While y goes from, where does y start? 0 up to x cubed. I like it. And what's going to be on the inside is the exact same thing. Because notice another thing that, not a lot of people do this, but the inner function doesn't give a shit what I just did. The inner function, what z does, and z doesn't change what it does just because I went like this. Look at it this way. Right? Z doesn't give a crap. It doesn't change the size of, the height of my roof doesn't change. Just because I decide to walk this way first instead of that way first. My roof doesn't go, whoa, shit, no. So it's still the same function. But notice what happens right off the bat. It's going to be a lot easier. So what's the integral of this dy?
This y.
Yeah, y times that. That's a constant related to y. And then I'm going to plug x cubed and 0 in, so I'm going to get x cubed, square root of x to the 4 plus 1. And of course then I can use, sure as all hell don't have to use trig sub. Yeah, it's just straight up u sub because I've got the inside, the function that's trapped, its derivative is out there. That's u sub. That's when you can use u sub. So u be the trapped part, du is related to the free part. Okay, maybe. All right. Let's see. Let's do that. So let u equal who? Then du is. I know, unfortunately, you've had teachers that taught you to solve for dx or some bullshit like that. That leads you to so many mistakes. How do I make a 4 show up in here? Put a 1/4 outside. That makes so much more sense because then I'm sure that I've got what I need. I've got 4x cubed dx. And of course, what happens to my limits when x is 0, u is 1. And when x is 2, u is?
32.
Nope. And this becomes u to the 1/2 du. And then, I mean, the rest is easy, hopefully, right? What's the integral of u to the 1/2? 2/3 u to the 3/2, right? And 2/3 times 1/4, yeah, is 1/6. And then I have to go from 1 to 17, and I get gross stuff here. I get 17 to the 3/2 power of LS. All right. So I want to show you at least one example of an actual function inside and what flipping the limits actually does for you. So here's something. It's always a question every time I teach 281 about what order I want to show you certain ideas in. So I decided this semester to start with where people make the most mistakes and to relate it to 180, something you already kind of know. Now let me take a step back and just tell you the concept behind what we accomplish when we do this shit. So for that, I'm going to need some help with drawing. You guys know that all too well. Okay. So I try to orient it so that you can see what you need to see. So it's kind of like turn around a little bit. But this is basically the way the X, Y, Z, right? So you guys with me? So this gray on top is the f of x, y. I love it. So it's the thickness here. So really what we're doing when we have an integral, so if I were to, can't do that, Jeff, at the same time. If I were to integrate this like this, that means that, I really want this to make sense. I integrate fully for some value of x. So let's say I'm going from, I think this x goes from 0 to 4 here. That's my sliders, right? So for x equal to 0, there is an area under this curve, right? For x equal to 0. And then watch. So for x equal to, just pick an x. I like how this moves along. Do you see what's happening there? So this is x equal to, let's try to get x equal to 1. That'd be nice. That'd be nice if I get 1. There, okay. I really want this to make sense. So this has to go for every value of x that's allowed. But for a single value of x, this integral is Math 180 integral. Do you see how this is just a plane, a slice of this? This is what you did in Math 180. So now what are we doing? We're adding up all of these areas. So how do I calculate this area? Well, I let x equal 1 in this case. Plug it in here and then integrate this, dy. Like Math 180, no problem. And then I do it again. So that gives me an entire area, that red area. And then I move a little bit. And then I do it again. And then I move a little bit. And then I add those all up. Well, I'm going to add up how many areas am I going to end up adding up? Infinite number. And of course, infinite sum is freaking integral. Right? So for every value of x, I'm going to get another slice area. Do a little infinitesimal step. Get another slice area. Get another slice area. Right? And just keep going through. So I love this idea of the double integral. The inner one is the one we're used to. And the outer one is really just accumulating all the freaking 180 integrals we're doing as we move across this. So we're scanning. But this scan is the one we're used to from 180. And this is really just adding up all the slices. That's almost too nice to believe. And of course, if I did it the other way, so this is, I step through and I get all those areas. And add them all up, and I get the volume under that surface. Right? Now, of course, I could do the other way around. step through that way instead, but it's the same stupid idea, right? Same idea. Do you guys get that? So that's the idea behind double integration and what it accomplishes, and the direct connection it has with what you do in 180. Maybe. So I don't know. I think I like that order of doing it. Every time I teach, I do it in a different order, but I like that order. To be honest, what we've done is we've done section 15.1 and 15.2 because we're crazy like that. 15.1. The reason I like to do this, the very first problem we started with was diagonal, a weird-ass triangle shape, right? That's the first one we did. The book and a lot of teachers start with rectangular areas in my XY plane, which leads students down the wrong path right off the start. So if my region in my XY plane was a rectangle, you with me? So this is what I'm integrating over. Then do you see how this is why people make so many mistakes if you teach it directly the way the book does? Because this interval could either be 1 to 4, 0 to 5, and what's this? What d who to what? So the inner one is dy dx. Is that cool? And turning it around really is just turning these stupid things around, because there's no walls really. They're all just number to number. I don't miss anything. But the minute I do this instead, and I say, no, I don't mean that. I mean this. Oh, shit. Now I can't just turn them around because one wall is controlled by a variable, and I have to actually flip that around. So 15.1 is, compared to what we've done today, 15.1 is easy. If you let it be. 15.2 is really more like what we've been doing today, where you have to be careful with the walls, how they define, is it x equal function of y or the other way around? That's 15.2. Last thing for today. Another thing that's in 15.1. Mario, can you bring those lights? Thanks, man. Last thing. And I'm realizing that the order I'm doing this in is an order I'd like, but it's exact reverse order of how this was constructed. But it's beautiful. You do it differently when you teach than when you construct. So, if I have some region, and over that region is some surface, right? So I got some surface over that region. Oh, that's horrible. Oh well. Try to do something a little better. Let's see what I can do here. You can do it, Jeff. Yeah, let's just do that. Let me see if I can get away with that. So it's over that region. You with me? All right. A little bit. All right. Yeah, a little. All right. Now remember in 180. We're not going to do this all. I told you already. We did this kind of thing, remember? And you had, like, they were defined left endpoint or right endpoint, all that kind of crap. And then you let the rectangles go to infinity. Well, you do the exact same thing here, except instead of rectangles, you're going to make rectangular solids. So you're going to have, like, for example, you're going to break this up into these little grids. So let me just take one, for example, and it's going to go, each one of these sides is going to go up to, well, it's hard to show that. It's got a better picture in the book, right? Let's see if I can cheat a little bit. Oh, I know how to do this. Let's see. Yeah, I have to make a really long cube. All right, somehow it's going to work. All right, just pretend like it's a cube. So I've got this rectangular solid. The idea is what's important. I've got this rectangular solid. Now notice, I've got a lot, like here, remember you could do left endpoint, right endpoint, midpoint. Hopefully a teacher actually talked about the fact that you could do arbitrary points. Because what's going to happen is if you just make it arbitrary, but you let them go to infinity, you eventually don't have any choice. So who gives a shit what you do in the meantime? You're eventually going to lose all your choices. So here, what we normally do I might have assigned one problem like this, but because I wasn't that, I could do any corner. Do you understand? The height can be determined by the function value at any corner or midpoint. That's really the mostly what we do. But to be honest, I have this whole area to work with, right? So depending on how many rectangles, or in this case rectangular solids, I want to use to approximate my volume, it changes the area I've got to work with. You guys kind of with me? So my XY plane, this would look like this puddle. And I'm breaking that puddle up into little squares, right? Maybe I'm overdoing it or whatever. We're used to that kind of idea. And then I'm using, maybe every time I'm using the bottom right-hand corner to describe the height. I like it. And that might be an overestimate, an underestimate. The more rectangles, the more squares I use in my XY plane, the better the resolution is no matter what. All that stuff is still the same. That's why I'm not going to go too deep in this, because you've done it already in 180. It's very similar, the steps you go through Riemann sum-wise. So eventually you end up getting a double sum, because you have to sum this way and that way. And that leads to the double interval idea. So that part I'm going to let you look at yourself in 15.1. They obviously do a much better job with the pictures. Just to show you an example what I mean. There, see? So much nicer there. So you get this nice little rectangular solid, and if you add them all up, you get an approximation for the volume.
We're not going to draw that.
No, I got it. Here's your double sum. You guys see that? Your double sum. I could be the rows and J could be the columns. So the idea is really simple. It directly connects to what you did in 180. I'm not going to do much more than what I just did. Here's an example of the different corners you could use to determine the height for each region. All right. All right, guys, that's enough. So we did up through 15.2. What's up?